Now we're going to move on to a new section, the comparison test. The idea behind a comparison test is that if you have a function, so if you have a function that you know is always bigger or equal to another function, then if the integral of the big function converges, then the integral of the smaller function will also converge. So for example, here you know that f of x is always bigger or equal to g of x here. Now, if the integral, remember the integral is the area from a all the way to infinity. So from a so the integral is the area underneath the function. So if you know this function here, if you happen to know that this function converge, then g of x, because g of x is always smaller, then the area of g of x will also converge. So the area of the blue line here, the area underneath the blue line, will also converge. So if you look at this, hang on. If let's say if you know f of x is always bigger or equal to g of x. Now, if g of x, if the integral of g of x diverges, so we're saying this is g of x. G of x, don't forget, is the smaller one. If g of x diverges, then f of x will have no choice but also to diverge. Because f of x must always be greater than g of x, it must also diverge. It can't converge, because here, if you look at this here, f of x. So this is our f of x here. F of x here is actually, well, f of x must always be greater or equal to g of x. So if you happen to know that g of x diverge, then f of x, because f of x must always be greater than g of x. If the integral of g of x diverge, then the integral of f of x must also diverge, because f of x must always be greater or equal to g of x. So hang on, let's start again. So if f of x is always greater than g of x, so if f of x is always greater or equal to g of x, then if you happen to know that this converge, if you happen to know that the bigger one converge, then the smaller one will have no choice but to also converge. Now, if you have this scenario here, where the smaller function, if you happen to know that the smaller function diverge, the integral of the smaller function diverge. If you happen to know that the integral, remember the integral is the area underneath it. If you happen to know that the area underneath the smaller function diverge, then the upper function, the integral of the upper function, must also diverge. Now, if you look at this scenario here, where if you if f of x, if the integral of f of x diverge, then you can't deduce anything in this case, because g of x, this is g of x. If g of x is smaller, it could converge, or g of x could also diverge. So in a case where the upper function diverge, there are two scenarios could happen. G of x could converge, or g of x could diverge. So you can't deduce anything when the integral of f of x dx diverge. If this thing here diverges, you can't deduce anything. Hang on, let's go back to here. Up here we're saying f of x converge. So here you can deduce something. If f of x here converge, if the bigger one converge, then the smaller one must also converge. Down here, what I'm saying down here is that if f of x diverge, remember f of x is a bigger one of the two. If f of x diverge, then you can't really deduce anything, because the smaller one could converge or it could diverge. So you can't, in this case here, you can't deduce anything if you know this diverges. If you know the integral of this diverge, you can't really deduce anything. Now, the same goes for this. If you know the smaller one converge, then you can't really deduce anything, because f of x being bigger than g of x, f of x could converge or it could diverge. So if the smaller one converge, then you can't really deduce anything. if the bigger, yeah, if the smaller one converge, then you can't really deduce anything because the bigger one could converge or it could diverge. The idea behind the comparison test is this: if here we don't know how to integrate this, but we can deduce if it converges or if it diverges. So the idea behind a comparison test is that you you realize that well, in some of the earlier videos we've seen that this here converges. The integral of 1 over x squared converges. We've seen this. So the idea here is that 1 over x squared is always bigger or equal to this thing here, because here you've got 1 over x and then you plus a tiny amount. Remember, your sign oscillates between 1 and negative 1. Now when you power it to when you get a number, then you power it to the power 4, it will remain, this number here will be between 1 and 0, because if sine of x is always oscillating between 1 and negative 1, let's say this here, let's say currently is at negative 0.3, say, then negative 0.3 to the power 4, then that number, well, the biggest it would be 1 to the power 4. That's the biggest one. Well, this one here, well, the point here is that this thing here is always trapped between 0 and 1. This thing here is always trapped between 0 and 1. Well, here, so you've got the exact same thing, but then you're dividing it by a tiny bit more. So the point here is that this thing here will always be bigger or equal to this thing here. Now, if you look at this, this thing here it looks something like this, and you know it converges. Well, this thing here being smaller, I don't know what it looks like. Maybe it looks something like this. But if this thing here converges, if the integral of 1 over x converges, then this thing here will have no choice but also to converge. So the idea behind this comparison test is that we don't understand how, we don't know how to integrate this, but we can deduce whether or not it converges or diverges. So the trick here is to realize that this thing here is always less than or equal to this thing here. Well, we know that the integral of 1 over x converge. So as this is always smaller than this, then this has no choice but to also converge. So I will give you an example in the next video.